Okay, this is our Physics 212 Project 1 by Parker Young, Tyler Semich, and Colin View. Problem we chose is the turntable, and this is what we were given. A box of mass m is positioned at the edge of a frictionless turntable of radius r that is rotating at a constant angular speed. An ideal string passing over a massless pulley and through a hole in the middle of the table connects the box to a hollow ball of mass m and radius r with the string wrapped many times around the edge of the ball. And we need to find the angular speed of the turntable. Understanding the problem, part 1. In this equation, we are given the mass of the box m and the turntable radius big R. And the turntable is rotating at a constant angular speed. Then we have a string passing over a massless pulley and a ball with mass little m and radius little r, with the string also wrapping many times around the ball. Understand the problem, part 2. Assumptions. In this experiment, we are assuming that we are using Earth's gravity. Air resistance is close to negligible or does not affect the experiment at all. The surface of all objects are frictionless. The pulley is massless. The string being used is ideal. There is uniform mass distribution, and angular motion is conserved the entire time. Here are free body diagrams we drew for this. First, this is a picture that we were given, where we have m, the mass of the block. We have a force, normal force going up, force and gravity going down. Then we have a tension force going around this pulley and down to the ball. We have mass little m and radius little r. Here, this is a view from the top of this same picture where we have the same variables of r, big R. Over here, we have acceleration centripetal, and acceleration in the tangential. These pictures we got off the internet, which this is for the block, the inertia of the block, inertia of the turntable, and inertia of the ball. But we only need this one for our equation, which is I equals 2/3 mr squared.
All right, so in this problem, we're going to be using Newton's second law equations a lot, like F net equals ma and F net equals mass times gravity minus the force of tension. And we're also going to be using some torque equations, like the net torque is equal to inertia times the angular acceleration, and torque is equal to R times F. And we have 3 moments of inertia for the total system, but the one we're going to be focusing on is the inertia of the ball. And this equation can be shown by 2/3 mr squared. And yeah, so getting into solving it, we start with solving the net torque, which is R times the force of tension equals inertia times angular acceleration. And manipulating this, we can set torque as R times force of tension, and we can set that equal to I to inertia times the angular acceleration, which is A over R. And so plugging in 2/3 mr squared for I, we get force of tension is equal to 2/3 mr squared times acceleration all over R squared. And canceling out R squared, we get force of tension equals 2/3 times mass times acceleration. And so next we can look at the net force, and we set that equal to mass times acceleration, which is also equal to mass times gravity minus the force of tension. And so rearranging this, we can set it as mass times acceleration is equal to mass times gravity minus 2/3 mass times acceleration. And dividing out masses, we end up getting acceleration is equal to 3/5 times gravity. And next, we set the value of the force of tension we got, and we use that value and plug in 3/5 g for as our acceleration, and we get force of tension is equal to 6/15 mass times gravity. And simplifying that, we get 2/5 mass times gravity. And so next, we can set the force of tension equal to the mass of the block times centripetal acceleration. And we know centripetal acceleration is v squared over r, so we end up getting force of tension is equal to the mass of the block times v squared over r. And then we can set the force of tensions equal to each other, and we get 2/5 mg is equal to m times v squared over r. And we know that v is equal to w. We know that v is equal to w times r. So using that, we can set it to 2/5 mass times gravity is equal to the mass of the block times w squared r squared all over r. And simplifying that, we can get w squared is equal to 2/5 mass times gravity of the ball and all over mass times the radius of the block. And taking the square root of both sides, we end up getting the angular velocity is equal to the square root of 2 times mass times gravity all over 5 times mass times the radius of the block. So plugging in numbers, we can make some assumptions about the weights of the boxes and the ball and the radius. And so we can just say the mass of the box is 10 kilograms, gravity is 9.81 meters per second, mass of the ball is 5 kilograms, and the radius between the pulley and the box is 3 meters. And so plugging that into the equation, we get an angular velocity of 0.809 radians per second.
Okay, so for sense making, I guess for the unit check, for angular velocity, we for angular velocity, it's basically confirmed that's radians per second. We find this by converting the certain variables into units. So the mass should be kilograms. So as you can see in the second equation, both masses are turned into kilograms. Gravity is basically acceleration, so it's basically m over s squared. The radius should just be meters. So crossing both of them, crossing from the numerator and denominator, we can take out the kilograms and the mass or the meters because they're already we're just canceling them out. That eventually just turns into 1 over second squared, which since there's no unit on top, we can assume or just say that there's radians, and then that eventually just turns into radians over second, which is the unit for angular velocity. Okay, sense making for numeric value. We solved the original problem or equation with a radius of 3. We got 0.809 radians per second. We want to see what will happen to the angular velocity if we increase the radius. So we change the radius from 3 meters to 100 meters. And as you can see from the calculation picture on the screen, it reduced the angular velocity pretty significantly. This makes sense because as the radius increases, the angular speed slows. And as the radius decreases, the angular speed increases. This makes sense as the radius is in the denominator, which shrinks or grows the final or just the angular velocity. Even if the angular velocity increases or decreases, it remains constant and should conserve angular velocity. Reflections. When we first saw this problem, we thought of the problem or activity from homework activity 2. In this problem, we wanted to find kinetic energy and how it changes. This is different from what we found in the project, which wanted the angular velocity of the turntable. Another difference is that it didn't have a string or a hollow ball. It just had a disc and brick, which is related to the block and turntable. This problem helped us determine how to use the moment of inertia and how we determine the angular momentum, which the total momentum is 0 and the initial and final momentum should be the same. Another activity that we found to be related to this project is activity 4-2 from studio in week 2 or week 4. We dropped 2 spools, one that is free to rotate and one that is not. They both dropped at the same speed, but had different rules and equation applied to it. This activity helped us understand how the hollow ball should have worked in this project and how it would affect this whole experiment. This also helped us determine which moment of inertia we should use.